All right, continuing our discussion of waves, we've got the two types here. We've got the transverse waves, which is what we usually tend to think of because we can easily visualize this the wave going up and down and up and down. These are almost like waves in the ocean. But then we have these longitudinal waves where we have alternating areas of compression and expansion. And those longitudinal waves are important because that's the way that sound waves travel. So sound waves are caused by some type of vibration. In this diagram here, we're showing a drum membrane that's vibrating back and forth, and it causes these areas where the air particles get pushed together to form a compression area, and then we have these alternating areas where they're spread apart. So we have compression, expansion, and those waves of compression and expansion reach our eardrums, and that's how we hear sound, because those waves vibrate the eardrum. So again, waves are a way to transport energy. The medium itself is not moving, it's the energy moving through the medium. And a way we can quantify the amount of energy transported by a wave is by the wave's intensity. So intensity is energy per time over area, and energy over time is power. So it's power over area. So if you think of like a square on a wall, what we're measuring is how much energy is hitting that square due to the wave. So we have to kind of measure it in a per square meter area. Okay, and intensity is related to the amplitude of a wave. The higher the amplitude, the more the intensity, but they're not exactly the same. They're just proportional. So intensity is directly proportional to the amplitude squared. So we've got to square the amplitude in order, sorry, the amplitude squared will cause an increase in intensity. Another thing that the intensity of a wave is directly proportional to is 1 over the distance squared. So you could say that the intensity is inversely proportional to the radius squared. So if we have our sound wave source here in the middle, it goes out in all directions. That's why it looks like a sphere. We tend to think of sound waves traveling in just one direction, but they're actually going out in all directions simultaneously. The farther you get away from the source of the sound, the less intensity it has. So if you are right here, let's say this distance is 2, and this distance is twice that, it's 4. Actually, let's make this a little simpler. Let's make this distance 1 and this distance 2. 1 over 2 squared is 1/4. So the intensity at this distance would be 1/4 of the intensity at this distance r1, assuming that the second distance is double the first. So the intensity drops off quickly due to that exponent. So the farther you get away from a sound source, the more quickly that intensity drops off, which makes sense. Okay, so I know this is a pretty big, complicated looking formula here, and it is. But this is for the energy carried by a wave. So again, we need to look at the energy being transported through a rectangular area here. So the medium that it's passing through has a length L, and that length is equal to the velocity times time, how quickly the wave passes through that material. And we have this material has some type of density, whether we're talking about air or water or any other material. We can look up the density rho. So we've got the velocity of the wave, the frequency of the wave. S, in this case, is used for the surface area. Why not A? Well, because A is being used for amplitude, and T is time, how quickly the wave passes through that material. So when we take all those things into consideration, 2 pi squared times density times surface area times velocity times time times frequency squared times amplitude squared. I know that's a lot of variables, but we're just multiplying them all together, or squaring a couple of them, gives us the energy carried by a wave. Okay? And we can also look at the intensity of the wave, assuming that we're going through a constant medium of a homogeneous density. Then the intensity of that wave is 2 pi squared times density times velocity times frequency squared times area squared. That's another big equation, not quite as big as the last one, but that will tell us the intensity of a wave. Okay, so I said earlier when we were looking at a rope with a wave pulse traveling down it, that it would come down and back. And then I corrected myself to say, well, I guess that kind of depends on how it is being held in place. If it's fixed here, we've got like a nail or a tack holding this wave still. What will happen is that wave pulse will work its way down, it'll get to the end, and then it will reflect or bounce back. The difference being that the reflected wave will be below the horizontal line here of the rope, where the wave came in from above. If it's free, if the other end is free to move here, then the wave will travel down, hit the end, and may bounce back and be on the same side of the rope. So the summary here is that a wave can be reflected when it reaches the end of the medium that it's traveling through, and in the case of a rope, if it's held still, the wave gets inverted. If the end is free to move, it will still reflect, but will maintain the side of the rope that it started on. If we have a light rope connected to a heavy rope, this is sort of a representation of what happens when a wave is traveling through a medium and the density changes. You could think of this maybe as being like air and water, are just two examples I thought of here. So something light and something heavy. When that wave hits the point where the medium changes, part of that wave is going to be reflected back, and part of it will continue to be transmitted into the new medium. The amplitude will be decreased because some of that energy went back this way. Again, this amplitude will be decreased as well. So we had a nice tall wave here with a big amplitude. It hits a change in medium. Some of it is transmitted, some of it is reflected. Each of these waves have amplitudes lower than what it started with. The total amount of energy doesn't change. It just gets split up. When sound waves bounce off of a flat surface, they are reflected just like a physical object would be. Like if we had a tennis ball bouncing against the wall, we have the angle of incidence measured to this imaginary plane that's perpendicular to the surface, and the incidence of reflection. Those two angles are equal to each other. So at whatever angle the sound wave comes in at is the same angle it will bounce off at. Now, what happens if you have two waves traveling towards each other on a rope? One is on the positive side and one's on the negative side of the rope. What happens when these two waves come in contact with each other in the middle of our rope? Well, in this case, where they're both on opposite sides of the rope, when they meet each other, we have what's called destructive interference. Essentially, they cancel each other out. So when they overlap for an instant, there is no wave at all on this rope. Then they pass through each other. The one that was on the bottom continues to the left on the bottom, and the one that was on the top continues to the right along the top. So they pass by each other after coming into contact with each other. But for that brief instant where they do come in contact with each other, they have what's called destructive interference. In this case, we have two positive waves, both on the positive side of the rope. What happens when they come in contact with each other? Well, the amplitude here would be double what the amplitude was before. We had an amplitude here, they come together, and this is what we call constructive interference. So they essentially double the magnitude of the amplitude, and then they continue on their way here. So one to the left and one to the right. So waves that come in contact with each other will interfere with each other, and depending on whether they're both positive or one's positive and the other's negative, they will exhibit either positive or rather constructive or destructive interference. So here we have two waves, both reaching peaks at the same time. So these two waves, if they were to come in contact with each other, would have constructive interference. So the amplitude is getting bigger. Here, where the first wave is at its peak, the other one is at its lowest point. If they have the same amplitude and same wavelength, they're going to destructively interfere with each other, and that is going to cancel the two out. And so we end up with this flat wave here that's been completely canceled out. And then here, when this wave is at its peak, this wave is at 0. So they're one is shifted over slightly from the other. And in this particular case, these two waves don't interfere with each other at all, because when one is at its peak, the other one is 0. So if we think of this amplitude as being 1, and this is 0, 1 plus 0 is just 1. So we end up with a wave at the top, and it comes down. And so we ended up with a wave here that looks pretty much just like this one, the one that we started with, because of the way that the two are shifted over from each other. Some terminology about waves. If we were to connect a rope to the wall and we were to get the frequency just right, moving this rope up and down so that we had a wave that just went up and down, there didn't seem to be a pulse. So we're not talking about a little pulse that seems to visually travel down the wave, but we get it just so that the rope goes up and down, almost like we're playing jump rope. This is what's called a standing wave. So a standing wave is one that, visually looking at it, it doesn't appear to be traveling down the length of the rope. The rope just seems to be going up and down, up and down. And glancing at my timer down here, I'm about to run out of time. So I'm going to have to cut this off and pick it up in the next video.